That's the first thing that happened. The class began and the first recording sound in the class is someone sneezing. All right. Okay, guys. We have 1 minute. So this is your last 15 or 30 seconds to ask questions, sneeze, whatever. Okay, the links for H1 right up on the web page seem down for you. Is it? Post that on Piazza, and somebody will answer. All right, so let me begin. Right, what we've done so far is to introduce the concept of what a neural network is, a little bit of history. And we've shown that neural networks are universal approximators. What we meant by universal approximators is that regardless of the kind of function you give me, so actually I think this answers one of the questions that came up earlier. So regardless of the kind of function you give me, I can compose a neural network that approximates that function to arbitrary. I can compose a network that computes that function to arbitrary precision. But the keyword is can. The question is how? How do I compose this network? That's what we're going to begin talking about in the next few classes. So we're going to talk about training neural networks. The topics for today and the next several classes, we're going to talk about the problem of learning. Today we're going to talk about learning perceptrons. There are slides on greedy solutions for classification networks, Adaline and Madaline. And we're going to look at the concept of empirical risk minimization, and we'll begin introducing the ideas of function optimization and gradient descent, or at least ideas related to these. So here's what we know so far. Neural networks are universal approximators. They can model any Boolean function, any classification function, or any real-valued function, so long as they have the minimal architecture needed to model the function. So guys, if you see me turning back and forth, it's because my tablet, which is the machine I'm working from, is to my right. I have Zoom running on a second machine just so that you can see my face, okay? So anyway, going back to our problem, when we looked at all of the various tasks, whether it was speech recognition, image captioning, playing games, all of these were these boxes which took some input and computed some output. And these boxes are basically functions. And these, therefore, can be modeled by neural networks, because neural networks are universal approximators. But then, some noise, someone, guys, please mute your mics, fellows. Yeah, okay. So, but then we must begin considering the mechanics of composing these networks. The network as a function operates on numbers. It takes in numbers and outputs numbers. That is the nature of mathematical function. So for this network to perform all of these tasks, all the inputs and outputs that we saw, the voice signal and its transcription, the image and its caption, the game state and the next game state, these must all somehow be represented as numbers. So our first question is, how do we represent these things as numbers? In general, how do we represent the input to the network, and how do we represent the output of the network in numeric form such that these machines can operate on them? And also, we know that the network as a universal approximator can compose functions that perform all of the tasks above. But then how do we actually compose the network that performs these tasks? For today, we are going to focus on the second issue. How do we compose a network that computes the requisite function? We'll answer these first two questions later. So some preliminaries first. Let's begin by looking at the basic units of our network. The network is a multi-layer perceptron. So the basic unit is the perceptron. Here's the perceptron. It operates on real-valued inputs, and then first computes an affine function of the inputs, which is a weighted sum plus a bias. And this affine function, which I'm generally going to represent as z in all of my slides and in all the lectures, is put through an activation function. And the most basic activation function that we saw was the threshold activation, which outputs a 1 if the input is, if Z is positive and 0 otherwise. But then in reality, the activation function can be anything at all. The output of the perceptron is the output of the activation function. The parameters of the perceptron, which decide how this perceptron behaves, are the weights and the bias. Now, just as a matter of representation, instead of having an explicit bias, we can also think of the neuron as having, I'm randomly going to use the word neuron or perceptron, they mean the same thing. So we can think of the neuron as having an additional input, which is always fixed to 1, in which case the weight corresponding to this input becomes the bias. So this picture and this picture are the same one. Instead of having a bias going, I can say that there's an input whose constant input of 1, and the weight corresponding to it is the bias. And this representation is convenient because then I don't have to distinguish between the weights and biases. So anytime in my slides, when you don't see an explicit bias, you must assume that I'm using this representation. Now, first, the structure of the network. The entire network, of course, is a network of perceptrons. We're going to assume a feed-forward network, which means that computations are performed in a strictly directed way, proceeding unidirectionally from input to the output, left to right in this figure, or bottom to top in this figure. So when we process an input, each neuron in this network is computed exactly once. It means the output of a neuron never loops back and goes back into it ever for a given input. Now, a major part of designing such a network is the architecture of the network. How many layers does it have? How many neurons in each layer? How these neurons are connected, and so on. For now, I'm going to assume that the architecture of the network is known, and the architecture that we have for the network is capable of representing the needed function. So somebody mute your mic, right? So remember that we saw in the last class that that if the network doesn't have sufficient architecture, it simply cannot approximate the function. We simply cannot model the function. Here we're going to assume that the architecture is given and is capable of representing the function. That's the assumption we can work with. So what we learn are the parameters of the network. The entire network is a function. It takes an input. It produces an output. The parameters of the function are the weights and the biases of the neurons in the network, which are represented by blue arrows over here. And because this is a function, it's a mathematical object. So I can represent it as f of x semicolon w, where x is the input and w are the parameters of the function, which are the network parameters over here. So to model any specific function with a network, what we have to do now is to set these parameters, determine the w, such that, with that, when the network is composed with those weights, that network computes the specific function that we're interested in. So when we speak of learning the network, we are speaking of finding the weights and biases such that the network computes the desired function. And so having set those basics in place, I'll pause for a few seconds for any questions and then I'll move on. Any questions? Was this clear? Raise your hands. Nothing fancy, right? All of this was fairly simple. Okay, lower your hands, please. Now, so what we know is that given any function at all, we can construct an MLP that computes it. But then the question is, how do we compute it? So if somebody gave me a function of this kind, in this picture, it's a function over a two-dimensional input. Somebody gave me this function. How do I construct an MLP that computes this function? Now, one solution is to try to do it by hand. We've seen this in the class earlier. For example, let's say I want to compose an MLP to compute this diamond-shaped decision boundary over two-dimensional inputs. then we can do it with a network that uses threshold activations. We saw that in the last class. What we would do is to first construct a perceptron for this boundary over here. This is a line with a slope of 1 that goes through -1, 0, and 0, 1. Also, if we plug any value over here into the equation for this line, you want the result to be positive. If you plug any value from this region, you want the result to be negative. So if you work it out, it's very trivial. You'll find that a line that satisfies these conditions is x1 minus x2 plus 1 equals 0, which gives us this perceptron to capture this line. The weights for x1 and x2 are 1 and -1, and the bias is y. So we can literally handcraft this perceptron for this line. And similarly, I can compose a perceptron for this line. I can compose a perceptron for this line. I can compose a perceptron for this line. And then I can finally add an AND on top, which compares the sum of the 4 outputs of the 4 perceptrons to a threshold. And voila, I have this. What happened here? This is terrible. Now I have no idea how to get rid of this. And so voila, I have this decision boundary. Again, the reason I could actually do this, I could construct this kind of network for this decision boundary is that I know the decision boundaries. And the problem itself is very simple. A diamond-shaped decision boundary is quite trivial. For something even slightly more complex, this becomes infeasible. So back to the drawing board. Better option. Wait, what's this? Right. So a better option is this. You're given this function g of x. We want the model, and we want to derive the model parameters of this model such that this model computes this function g of x. Again, we are assuming that the architecture of the network is given and it's capable of modeling this function. So here's how we would do it. Let me try to do this with a figure, right? So I'm going to use a one-dimensional illustration. So let's say I have an input x, and this is the output. Now I want to, I'm given a target function, this one, which is my g of x. This is my g of x. Now I want to construct a network which exactly computes g of x. Now now again, remember that the network really is a function of its weights, right? So for any given setting of the weights, the network is going to compose some function. So let's say the network composes this function, right? Now this function, this is this is my network, neural network. This is not the function that this f is not the function that I'm trying to model. It is not g. So there is this error. And what I will try to do is to learn the parameters of the network to minimize this error. Now, the error is an area, right? So I need to quantify this area. To quantify this area, the first thing I will do is to quantify the difference between the actual, come on. I have no idea what's happening here. All right, fine, go away. I'm going to try to do this. Okay. I'm going to try to quantify the error between the actual output of the network, which is this, and the desired output of the network, which is this. To quantify this, I will define a function, a divergence between the desired value at x and the actual value of the network at x. I'm having troubles with my screen here, guys, so bear with me. I don't even know how to get rid of this ruler. Go away. Okay, so and this area then over here, this divergence function, which is divergence between g of x and f of x, f of, oh my good God, What is wrong with Microsoft? Okay, which is f of x semicolon w, right? So this divergence quantifies this difference. So if I can compute the difference at one location, what is this area going to be? Can anybody tell me? Anyone? What will the area be?
Integration of all the
It's going to be the
integral.
integral, right? Integral over all of x, the divergence between g of x and f of x dx. And so what I will actually try to do is to uh, minimize this. Uh, I will actually define this divergence. And now the area over there is defined by this integral. I'm going to try to find the set of weights that minimizes this integral. Ideally, now the divergence should have a very specific property. This divergence will be greater than 0 if the two values are not identical, and it will be 0 if the two values are identical. It doesn't matter whether the blue line is on top of the green line or the green line is on top of the blue line, the divergence will be positive so long as the two are not the same. When the two are the same, like over here, the divergence will be 0. So that's going to be the property of the divergence. And the integral of the divergence captures the area, which tells you how wrong the network is. And we're going to try to estimate these weights to minimize the divergence. But then, what is the problem over here? If I want to minimize this divergence, what do I need? What are the things I need? Anyone?
The value of the function at every instance.
I need the value of g of x everywhere, right? And I don't have that. So directly computing this is going to be impossible and we cannot minimize it. So instead, what we will do is to take samples of the function at different locations. So at various x values, we're going to compute we're going to get f, x and g of x pairs. And so now we have a number of samples of the function. So maybe I can just draw that differently, right? I have my x again, and I have my g of x, which is the function I'm trying to model. And what I will have is, instead of having all of g of x, I'm going to have just the values of g of x at some locations. x1, g of x1, x2, g of x2, and so on. These are what I'm calling my training instances. And then I'm going to try to determine the parameters of the network such that at x1, it correctly computes g of x1. At x2, it correctly computes g of x2, and so on. And then I'm going to hope that if I match the input-output relationships at these locations, that the network will also capture the value of the function in other locations. Now, this is just a matter of hope. It's not going to, there is no reason for you to believe that this hope will actually hold, but that's basically how we go about it. And so, and how exactly do we collect these samples? This is just basically gathering training data. For example, gathering sets of images and their class labels, or speech recordings and their transcriptions. Now, these samples are our training samples. And now we must learn the entire function from just these samples. We don't have the g of x. So we must learn the entire network from just these samples by learning the weights that correctly compute these outputs at these inputs. And the hope is that if you correctly compute the outputs at these inputs, the network ends up learning the function that you actually wanted to learn. Now,
Professor?
Yeah.
Sorry to interrupt. Can you please make me a host so I can set up the poll?
Wait, there was a poll at, yes. I'll take care of it right now because I don't know how to do it at this point, right? So here's the story so far. So what we're going to do is we're going to learn the network parameters to fit these training points exactly. Again, assuming that the network architecture is sufficient for such a fit. And we're assuming that at any input x, the value of the function that we have got, which is what we're going to call the desired output of the network at this x, is unique at every x. And hopefully learning to fit the function with the network at these input or at these locations will give you a function that models the actual target function everywhere. So that's a hope, right? So here's the story so far. When we speak of learning a network, we're speaking of determining the parameters of the network that are required for it to model a desired function. The network must have sufficient capacity to model the function. And ideally, we'd like to optimize the network to represent the desired function everywhere. However, this requires knowledge of the function everywhere. So instead, we draw input-output training instances from the function and estimate network parameters to fit the input-output relation at these instances and hope that it fits the function everywhere else as well. So, questions so far? Anyone?
Sorry, on the previous slide, why is the unique output important?
So this is an assumption I'm making, but think of it this way: the network is a deterministic function, correct?
Yeah.
Okay. So if I have two training samples and g of x is a function, if g of x is a function for any given input, there is just one output.
Oh, yeah.
So if you give me two guys, right, you have ambiguity over here. For now, we're going to assume that we're not dealing with ambiguity. We'll have to explain the ambiguity off with noise or something, okay? So anyway, so let's start with a very simple task. Learning a
Sorry,
classifier.
Professor.
Yeah.
I can hear a consistent background noise. I think someone else has just reported, but not sure whether we can mute everyone.
All participants are actually muted, except
I think
Riksha.
so. This might actually be my ceiling fan which squeaks. Okay.
Thank you.
All right. I'm going to be sweating for you kids, literally. Anyway, you'll have a video of me with a wet face. Now, okay, let's begin with a simple task, right? Learning a simple classifier. Now, this was amongst the earliest problems that people addressed using MLPs. And so we're going to specifically consider binary classification. Although what we discuss actually generalizes to multi-class classification as well. But then it's, oh my God, it's not letting me run the polls. Why is this not letting?
Sorry, I just wanted to interrupt you for 1 sec. I think the polls are from lecture 2 and there's no way of changing it.
Wait, no, this is, wait, I had entered the polls. I'm not sure what's going on.
Yeah, that's what, like we figured out that the polls are from lecture 2. That's what we wanted to tell you.
I had actually entered these yesterday. For some reason, these are missing. Okay.
Yeah, I think it's fine.
That's all right. So guys, we won't have polls today. It saves me time. Okay. This is Zoom problems. Okay.
Diksha, there were two questions on the chat.
Yeah.
The first one was if we do those samples need to satisfy Nyquist sampling theorem?
We are speaking of functions. So Nyquist sampling has to do with time series, right? Or series data. There's some function. You're just getting some. We're not speaking of. In fact, as you will find, it's highly unlikely that you're going to find anything that satisfies Nyquist. Okay, it's just samples. You're just reading input-output samples, and you're hoping that if you fit the function there, it fits everywhere. Right.
Yeah, and the second one, is it being sampled because we don't know every value of g of x? In other words, is this supposed to be analogous to how the training set cannot represent the entire true set?
The training set is a discrete set of values, correct? So will a discrete set of values represent the entire space? Sam, would it? Exactly, right? So you cannot, except for a very small number of functions in this world, the majority of functions, basically all functions, do not have a formula. You cannot characterize them formulaically, which means that you simply have no way of presenting it to a learning algorithm for the model to learn the function. The best you can do is to sort of get some input output values from the function. In the case of things like real value world tasks like image classification, it's literally the problem of gathering images and assigning labels to them, or gathering speech samples and assigning transcriptions to them. Okay. Okay. So let's start with the original MLP. We're going to start with the original MLP proposed by multilayer perceptron, proposed by Minsky, which is a network of threshold units. We'll see how to train this network using only a set of training instances of input-output pairs. Okay. Now let's take the simplest MLP, which is just a single perceptron. There is no a network; it just has one unit. The perceptron, as we know it, gives us a step function where the output is 0 on one side of the hyperplane and 1 on the other side, and we are trying to learn this step function. Okay. So, except in our setting, you're not going to be given the entire function. You're only given some input-output pairs like these blue and red dots. Each of these dots represents an XY pair, where X represents the coordinates of the input, and Y represents the desired output, which is either 0 or 1. And we must learn this function from only these pairs. Now, the output of the perceptron is given by this by now familiar formula. It's 1 when the affine, an affine function of the inputs is positive, and 0 otherwise. And the parameters of the perceptron are these weights and this bias. The classification boundary is the hyperplane that exactly satisfies this equality, where the affine function equals 0. And so this is a hyperplane such that all the red dots, which indicate class 1, lie on one side of the plane, and the blue dots lie on the other side. Now, for convenience, I'm going to restate the perceptron in this manner. I just add this extra input of 1, and now the bias becomes a weight. And in this representation now, I can say that this is no longer affine, this is linear, not just affine, it's linear. So whenever the weighted sum of all of the inputs is positive, the perceptron is going to output a 1, otherwise it's going to output a 0. Now, the boundary where summation Wi(xi) is exactly equal to 0, this is going to be a hyperplane through origin. Basically, what we did over here by adding this extra this extra bias is this extra input is, in the original case, maybe you had things like these, and so the decision boundary would not go through the origin. So we added an extra dimension. When we did this, then because from this extra dimension, all of them basically got this value of 1. So now all the data live on this plane, which is at height 1. And the data has maybe pluses over here and minuses over here. On this plane, the boundary is still not going through the origin, but in the higher 3-dimensional space, I can draw a slice of this kind, which does go through the origin. So that's what adding this extra bias, oh my God, does. Adding the extra bias, basically adding this extra input to consider the bias, converts this affine function to a linear function, and now the boundary is a hyperplane through the origin. Now, to find the perceptron that actually learns to classify these data points, what we really want to do is to find the equation of a hyperplane such that all the positive, the red dots, lie on one side, and all the blue dots lie on the other side. So before we continue, let's see how the classification rule works. Actually, let me draw this with a figure. It's easier. Now, when I have an equation of this kind, summation Wi xi equals 0, right? I can take all the weights and put them in a vector, w1 to wd. These are d dimensions. I can take all the inputs and put them through another vector, x1 through xd. So the summation wixi, let me call this w, let me call this x. So summation wixi is simply w transpose x. And this w is also now a vector, right? Now, what does it say for the product or inner product of two vectors to be 0? What does it say about the relationship between the two vectors?
Orthogonal.
They're orthogonal to one another, right? So this means that when I have, so if my weight vector is this w transpose x equals 0 is basically the equation of all x's that are at 90 degrees to this guy. So the weight vector is going to be orthogonal to the plane. And any point which lies on this plane is going to have this inner product, which is a weighted sum, being equal to 0. But then what if a point is on this side of the plane, the same side as the weights? Now, if the point is not orthogonal, what is W transpose X in this case? Anyone?
It's positive.
Yeah, but what's the value? It's going to be mod W, mod X, cos theta, correct? Where this is the theta. The theta is the angle between the vector and the weight vector. So if you have some input over here on the same side as W, these are of course positive numbers. Cos theta is going to be positive. So W transpose X is going to be greater than 0. What if you have a vector on the other side? Suppose I have a vector on this side. Then what is theta? This is theta, right? Going all the way over here. In this case, what is cos theta going to be? Positive or negative?
Negative.
Negative.
It's going to be negative, right? So basically for all vectors on this side, cos theta is going to be negative. And so you find that for data on this side, W transpose X is positive. On data on this side, W transpose X is negative. And so data which lie in the same direction as W are going to be assigned class 1, and data which lie on the other side are going to be assigned class 0. So that's how this whole entire classifier works. And so our problem of finding the perceptron for this data is that of finding the hyperplane, and is that of finding the W for the hyperplane that exactly separates the two classes. And specifically, you want the W to point in the direction of the positive class. Okay. Now, there's a very simple solution to this. What I'm going to do is to reflect every data point across the origin, like so. And once I reflect all of the data points across the origin, I'm going to end up with data of this kind. And because the data points have been reflected of the origin, now all of them, when I reflect the data point across the origin, because the decision boundary is going through the origin, the data point is going to cross the decision boundary and it's going to end up on the other side. Now, reflecting the data point across the origin is basically the same as negating every single component. So negating every single component is basically the same as saying I'm constructing a new vector x prime equals -1 times x. This I will only do for the negative class. And for the positive class, I'm going to say x prime equals x. So the red points stay on the red side, only the blue points get reflected, right? So I can generically write, if I use this, if I use a notation of, positive class equals +1 and the negative class equals -1, then I can say x prime, so y, the y for the positive class is +1 and for the negative class is -1, then I can just say x prime equals yx. This is the input, and this is the class label. So by using this +1 -1 class label, basically I can selectively perform the reflection for the negative instances by simply multiplying the each input by the class label. So did that make sense to everybody? Did this make sense, guys? Yes, no? Raise your hands. Right, all I've done is this. I've computed x prime equals yx, where the labels are +1 or -1, and that causes everything to get reflected across the boundary. So I'll wait for a second for people to raise hands. I want to see 100 hands raised so I can move ahead. So raise your hands, guys. That's 67, 70. I'm just counting. I'm seriously counting. So please, this has to make sense, right? And if you're not raising your hands, then probably you're not paying attention or you didn't get it. All right, I'll continue. So now all of the data points we know are guaranteed to lie on the correct side of the plane. So the problem is simply becomes that of finding a hyperplane through the origin, the problem of finding the decision boundary, once I reflect all the data points, is that of finding a hyperplane through the origin such that all the data points lie on one side of it. And this, if the classes are linearly separable, meaning if there is a hyperplane that separates the positive and the negative class, then such a plane will guaranteed exist. In fact, there's a very easy way of finding such a hyperplane. You just find the average of all of these x prime vectors. The x prime vectors are basically the ones where the negative class instances have been reflected across origin. So the weight vector is going to be the average of all of these guys, which is simply going to be the average of the product of the label and the data over the entire training set. Now, this is just one of the planes through origin that keeps everything on one side. You can find other planes, and you might apply other criteria like margin maximization to find the other hyperplanes and so on. The point is that this plane is easily found if the data are linearly separable. All you have to do is reflect the negative instances, find the average of all of the data at this point, and that weight vector is going to be the weight vector corresponding to the hyperplane that separates the positive and negative classes. Now, for linearly separable data, there's a better known solution, which was originally proposed by Rosenblatt. It's an online algorithm, which is the famous Perceptron algorithm. So here we initialize W and incrementally update it each time we find some training instance that has incorrectly classified. And this online algorithm is guaranteed to find the correct separating hyperplane for linearly separable data. Now, the algorithm itself is explained in detail on the slides, so I won't cover it in class. The point is that we know that when the classes are linearly separable, it's possible to find a hyperplane that cleanly separates the data quite easily. When the classes are not linearly separable, right? For example, I have a blue dot on the red side over here. In a situation like this, it's simply impossible for me to find a hyperplane that exactly separates the two data. There's no, it doesn't matter how I do it. If I, for some reason, reflect the data missing. So it doesn't matter how I do it. I simply cannot find a plane that exactly separates the red and the blue classes. So the summary is, for linearly separable data, a single perceptron is a sufficient model and can be easily learned. If the data are not linearly separable, it becomes a little more challenging, right? But here's the point. The sufficient model for linearly separable data is a single perceptron, and you can learn it very trivially. Now, suppose I have this data instead, right? This is a more complex problem, and it requires a full network. We want to learn an MLP for this classification boundary. We want the net to output 1 in the yellow regions. We want it to output 0 in all of the blue regions. But then we are only given these red and blue dots, and we have to learn the network from just these training samples. Now, we know from the previous class that this decision boundary can be perfectly modeled by a network with this architecture, provided it has the right weights and biases. You would have one subnet for the lower pentagon, another subnet for the upper pentagon. You can just OR their two outputs, and this network will model this decision boundary. But for that, the weights and the biases of this network must be properly set. So here's the question. I give you a network with a perfect architecture. Can we learn its parameters to represent this function from just the training data without, just the dots, using the perceptron learning algorithm? Now, to learn this pattern perfectly, each of these neurons in the first hidden layer must learn the decision boundaries shown by these lines. So, for example, one set of neurons, these guys will have to learn these purple decision boundaries so that this subnet can compose the lower pentagon. The other set of neurons will have to learn these gray decision boundaries so that this subnet can compose the upper pentagon. And only if we learn these boundaries properly can we subsequently construct these pentagonal decision boundaries and the overall decision boundary. So now what is the problem here? For simplicity, assume that from these data, I have managed to successfully learn all of these neurons, the weights and biases for these neurons. Only one perceptron remains to be learned. So I need to learn this perceptron. Now, the training data we have are what we have over here. The things in the two pentagons have read, are given class label 1. The ones outside the pentagons are class label 0. This perceptron can only model a linear decision boundary. So from this data, can we learn this perceptron? Anyone? Do you think we can learn this perceptron from this data? Obviously no, right? Because the the data are not linearly separable, right? What would we need to do? For this one, we'd actually know there's nothing you can do. The perceptron can only model linear boundaries, right? This perceptron will require data of this kind in order to learn this boundary. Whereas the data that we have are over here, right? Are what we had here. So what we are going to have to do is that to learn this perceptron, we are going to have to change the labels for some subset of the training instances. And this must be part of the learning. So what we must do is, to be able to learn this boundary, we must flip the label for some red data points to blue, some blue data points for red, such that the data points are linearly separable. And then from that, you learn this boundary, and only then the whole network is going to work, right? But what is the challenge over here? Anyone?
We don't know which points are to the other side of the line.
You don't know which data points must be labeled, right? So we'll have to, so how would we do it then? Remember, I'm assuming that all of these neurons are correctly learned. I'm just trying to learn this one. So what would the solution be?
Randomly?
For each.
Randomly, will that work?
I will have to do it.
Remove that neuron, run the network, and
Pardon me?
can we remove that neuron and run the rest of the networks through all the data points?
it's still not, it's going to be incomplete, right? It's not going to capture the decision boundary. What you would have to do is to test every single way of relabeling the data until you find one relabeling such that when you learn the perceptron from those relabeled data, the overall network correctly captures this decision boundary. Does that make sense? Right?
Makes sense.
So, in fact, we'll have to try out even when all the remaining neurons are learned and you're just trying to learn one neuron, you will have to try every possible way of relabeling the blue dots and the red dots such that we can learn a line that keeps all the red dots to one side. And now, in reality, you're going to be learning all the perceptrons. So which means that for every single one of these perceptrons, you're going to have to try every way of relabeling the data. What is the computational complexity of this? Anyone?
Exponential.
Exponential in what?
Data points.
Exponential in both the data points and the number of perceptrons, right? The product of the two. So this is simply not going to work, right? And so here is where we are. If we try to learn this entire network using the perceptron algorithm, even if our network has perfect architecture, we need to know the desired output of every neuron for every training instance to learn the neuron. And the desired output should be such that each neuron by itself has a linearly separable task to learn, and these linear boundaries combine to form the desired decision boundary. So we need to determine the correct relabeling. And if you get one single data point wrongly relabeled, that boundary is not going to be learned, and you're not going to be able to get this classifier. So that's how challenging the task is going to be. So this learning a multi-layer perceptron of this kind using the perceptron learning method is a combinatorial optimization problem. As part of training, we must now also determine the correct output for each neuron for every training instance. And this is at least exponential time complexity, right? So, and so what this means is that the perceptron learning rules cannot be directly used to learn an NLP. There's an exponential complexity of assigning intermediate labels. And if the classes are not linearly separable, it gets even worse. So this kind of stalled work on multi-layer perceptrons for a while. People tried various solutions, and as a workaround, Bernie Widrow proposed a greedy algorithm, which uses greedy search to learn the perceptrons. The algorithm to learn a single neuron is called Adaline, and the multi-layer perceptron extension of it is called Madaline. They're both very, very pretty algorithms. They're on the slides, and so they've been explained in quite some detail. I'm not going to go over them in class, but then please go over the slides and read up about them because these algorithms are going to feature in the quiz. So here's the story so far. Learning a network, which is the same as learning the weights and biases to compute a target function. It requires a network with sufficient capacity. In practice, we learn networks by fitting them to match input-output relations of training instances. A linear decision boundary can be learned by a single perceptron in linear time, right? If the classes are linearly separable. Non-linear decision boundaries require networks of perceptrons. But training an MLP with threshold function activation perceptrons will require knowledge of the input-output relation for every training instance for every perceptron in the network. And this has to be determined as part of training. So this means that this is an NP complexity combinatorial optimization problem. And that's a challenge, right? So the realization that learning an entire MLP was a combinatorial optimization problem stalled the development of neural networks for well over a decade. Now, the reason for this is this. The reason for why the perceptron with threshold activations cannot be learned has to do with the fact that the threshold activation is flat except at the boundary. So consider this. Let's say I have these two classes, 0 and plus, and this is the axes. And let's say I learned a decision boundary of this kind. Okay. Now, which way do I rotate the decision boundary to improve the classification? Which way must I rotate it? Left or
Left.
right? Left. Okay.
Left.
Now, suppose I'm using a threshold activation, right? If I rotate it only this much, is the total classification error going to go down?
No.
Right? What about here? Is the total classification error going to change?
No, you don't know exactly by how much you're
So the point is this:
switching.
if I go here, the error doesn't change. If I go here, the error doesn't change, right? So when I begin wiggling these weights, looking at the classification error doesn't tell me whether I'm going in the correct direction, because it doesn't change when I wiggle those weights just a little bit, right? It makes sense to you guys?
Makes sense.
Yeah.
Yes.
So here's the problem, right? This threshold activation is a flat function with zero derivative almost everywhere except at 0. So you can vary the weights quite a lot without changing the error, and it gives you no indication of which direction to change the weights to reduce the error. And if you have something more complicated like this one, then you have a whole collection of perceptrons, each of which are suffering from the same problem, in addition to the fact that you also have to determine the relabeling. So this is the entire MLP is a flat non-differentiable function, which means that the derivative is 0 almost everywhere. And it has, and at the boundaries, when it crosses a misclassified instance, the classification error jumps and the derivative is not defined. So this non-differentiability becomes a real problem. So we come up with a solution. What we are going to do is we are going to make the neurons differentiable with non-zero derivatives over much of the input space. Now, the threshold activation has 0 derivative everywhere, and at this point, it doesn't have a derivative. Instead, I'm going to use activations which have non-zero derivatives of this kind over much of the space. So rather than just using this threshold activation, I'm going to use activations of this kind. That way, when you change the weights even a little bit, this will result in a change in the output, even if the classification boundary itself doesn't cross a training instance. And then we'll get an idea of whether a particular incremental change to the weights improved the classifier or made it worse. So to understand, let's consider this example of one-dimensional data. So here, this is input. I have training data from the red data have class label 1, the blue data have class label 0. Consider a threshold activation. So initially I chose the threshold over here, okay? And I made one classification error. If I slide the threshold backwards in this direction from T1 to T2, at this point, what is the classification error? Anyone?
The same.
The same.
It's the same.
So sliding it backwards didn't change there. I don't get any indication of whether moving it back was a good thing to do. So instead, I'm going to use a different kind of activation, like this smooth function over here. This is a continuously varying curve which goes from 0 to 1. And my classification output, I'm going to call it 1 if this function is higher than 0.5, and 0 if this function is lower than 0.5. So this equivalent of the threshold t is the point at which the function crosses 0. Now you can see what is the classification error on this in this panel. How many mistakes is it making?
One.
One mistake.
Right? Just this one. What about here?
Still one.
It's still 1, right? But then instead of simply counting whether an instance has been classified as class 0 or class 1 correctly, I'm going to consider how much the target value is off from the curve, which is given by the length of these dotted lines. So over here, if I look at the total length of the dotted lines, which is the distance of the target value from the curve, where is it greater, to the left or the right?
Left.
Left.
To
The
right.
left is
So, right.
greater.
So when I slide the curve backwards, this total distance actually decreases. And that gives me a clue that sliding this curve backwards is a good thing to do. If I continue to slide it backward, the error is going to decrease, right? And so in derivative terms, we will find that the derivative of this total length with respect to the shift of this curve is with respect to the left shift of the curve is negative. When you shift the curve left, the total distance goes down. And this is a consequence of the fact that the activation function itself has non-zero derivative and it's graded in this manner. At any x, you can compute if the function decreases or increases if you shift it in either direction. So what we are going to do is to replace this threshold activation with continuous graded functions like the sigmoid or the ReLU or the soft plus. Now, the magic of this is that all of these activations are continuous. They are differentiable and they have non-zero derivatives almost everywhere. And even when they are not differentiable, like at this location for the ReLU, they are still continuous and have what are called subderivatives, which are basically bounds on the derivative that function like derivatives as for our purpose. I'll explain what subderivatives are in a couple of classes, but the point is that these functions are graded, they're continuous, and they have non-zero derivative almost everywhere. And of these in particular, the sigmoid activation is special. It's given by this formula over here. 1 over 1 plus e raised to minus z. The sigmoid, it's has this, come on, this auto resize nonsense on. Back to sum. So the sigmoid has this kind of shape. It goes from 0 to 1. The equation is 1 over 1 plus e raised to minus z. This is z, right? And what happens at z equals minus infinity? E raised to minus z equals e raised to infinity equals infinity, right? So 1 over 1 plus e raised to minus z equals 1 over infinity equals 0. So when z becomes a very large negative number, this goes to 0. Similarly, when z is plus infinity, then e raised to minus z equals e raised to minus infinity, which is 0. So 1 over 1 plus e raised to minus z equals 1 over 1, which is 1. So when z becomes very large, it becomes 1, and in between, it sort of smoothly goes from 0 to 1. And so this activation has a very nice interpretation, which is that it can be interpreted as the probability of class 1 at different x's. So, it's a very useful activation. This is just as an aside. There's a somewhat more detailed explanation of the intuition behind this on the slides. I'm going to skip it and leave it as readings, go through the slides, because the explanation will figure in the quiz. So anyway, getting back to our problem, the activation sigmoid, the activation function over here is a differentiable function of z, whichever one we chose. And specifically, the derivative is well defined almost everywhere and has non-zero values and is bounded. As a result, the output of the neuron is differentiable with respect to z. What this means is that for small perturbations of z, you will know you can compute the corresponding perturbation of y. Now, since z is simply a weighted sum of the inputs, z in turn is differentiable both with respect to the x's and the w's. And so using the chain rule, y is now differentiable with respect to the weights and the inputs. So what this means is that you can compute the change in the output for small changes in either the weights or the input. And this is what we're going to use. Now, as a result, each perceptron in the network is differentiable with respect to each of its weights and biases and its inputs. And when a perceptron is differentiable, it means that you can explicitly compute how the output changes for small perturbations of its input and of its weights. So, and you can compute the entire chain of such responses. So a small change in this weight is going to result in a small change in the output of this neuron, and you can compute exactly what that is going to be. A small change in the output of this neuron is going to result in small changes to the outputs of both of these neurons, and small changes to the outputs of these neurons is going to result in a small change of the output, which means that, and all of these changes are computable because this function is, these activations are differentiable, which means that you can compute how much a small change in W is going to change the output. And this holds for every parameter in the network. The overall function represented by the network is differentiable with respect to every parameter in the network using the chain rule. Small changes in these parameters result in measurable changes of the output, and you can compute the difference. So, and when you use non-thresholding activation functions, these derivatives are generally going to be non-zero for most inputs. Now, exactly how these derivatives are computed, we'll see later. But then the point is this, that now we can actually figure out how perturbing each of these guys changes the output, and we can use that to figure out how to modify the parameters of this network to make it fit a target function better. So here is the overall setting for learning the MLP. We are given a collection of input-output pairs where X in Xi di, Xi is the input, Di is the target output, the value that that you want the function to take. And both X and D may be vectors. We want to find the network parameters such that the network outputs this desired output whenever it gets the corresponding input, or at least a very close approximation to it. The architecture of the network must be specified by us. So the only terms to learn are these are the parameters of the network. Now, going back, right? Recall that the network itself is modeling a function. So when we are learning the network, we're actually trying to learn its parameters to minimize the total error between, I don't know if I. So when we learn the network, we are just trying to, okay, you have X, you have the target function g of x, and you have the network function f of x. You're trying to minimize this total error. That's how we're actually trying to learn the parameters of the network, right? Now, to do this, we've defined, again, remember, we've defined a divergence between the actual function value you want and the value that the network is currently giving you, which will be non-zero. If the two are not the same, it will be positive. Now, and we're trying to minimize, and that is this height, and we're trying to minimize this area of this error, the volume of error between the network and the actual function that you want to compute over the entire input space. Now, you can be a little more conservative. In general, remember, the network is only guaranteed to be an approximator. So keeping in mind that you're very unlikely to be able to learn a perfect, exact model for the function. You can take advantage of this and say, and focus on just those inputs that are going to be feasible. For example, if X never, you rarely ever see infinite inputs and outputs. So there's no point in computing the area out at infinity. If your input is guaranteed to always be positive, there's no point in computing this error over the negative side of the input space. So we can focus on minimizing this error in only the region of the space where the input actually happens. More generally, some values of x are going to be more frequent than others. And so it's more important to minimize the error at more frequent values of x than at less frequent ones. So instead of simply minimizing the error, this divergence, the volume of the divergence, you minimize the weighted error, where the weight given to the divergence at any point is the probability of the input x. So the modified error function looks like this integral over here, which is the integral over all x of the product of the divergence between the output of the network and the desired output of the network, and the probability of that x. So we're actually minimizing the area. We are actually minimizing the area or the volume of the weighted divergence. Now, this term over here, remember, this is a standard equation from probability. Anytime you have some f of x times p of x dx integrated over all of x, this is just the expected value of f of x. I'm assuming all of you are familiar with this. You recall this, right? This one, yes or no? Yeah, I mean, pretty much everybody should. So what we will do is compute the expected value of the divergence between the network and the target function. We're going to learn the weights to minimize this expected value. But then in reality, we can't actually compute it because we don't really have a complete specification of the target function. So again, remember that our solution for this was to compute a bunch of training samples, and we were trying to minimize the error between, we were trying to make the function network fit the values, target values at the training instances. Alternately stated, we can try to minimize the total length of the error at these training instances. And our hope is that if you minimize the total length of the error at these training instances, you'll be minimizing this volume itself. And that is basically what we're going to do. Now for this, we need to collect our training instances carefully, and provided you actually collect your training instances from the probability distribution for the data itself, this actually ends up having a very nice property, which is this, right? What we want, this is the expected divergence between the network and the function you want to model. Instead, you're approximating it by the average divergence at all of these training instances. You're approximating this volume by the sum of these lengths. Now, it turns out that this is actually a very sensible thing to do. Why? Because if I take the sum 1 over n of the divergence of f of xi and g of xi, which is the divergence at the ith training instance, I'm taking the average. And if I take the expectation of this guy, this is simply going to be 1 over n summation over I, the expectation of the divergence. Now, the expectation of the divergence is not a function of the input itself. So this is simply going to be 1 over n times n, because you're summing n of these. N is the number of training instances times the expectation, which is thus the expectation itself. So what this means is that provided you compute you gather your training data from draw the training data from the actual distribution of the data, then this average divergence over the training instances is what is called an unbiased estimate of this expected divergence. What we mean is that if you were to repeat this experiment many times, you went and collected, say, 1,000, if you decided to choose 1,000 training samples. So you repeated an experiment many times where each time you drew 1,000 training samples, and then you computed the average divergence. If you repeated this experiment many, many times, and then you computed the average of these average divergences, that is going to pretty much look like this guy here. So, this average, this expected divergence is what we will call the risk, the true risk. This is what we will call the empirical risk, because we are computing it from empirically drawn samples from the data. And the expected value of the empirical risk is the true risk. So this gives us a mathematical justification for saying, I'm going to minimize this guy. And because I know that on average, this guy is going to give me the same value as this, I can hope that minimizing this term here will also minimize this term to the left. And so what we actually perform is empirical risk minimization. You're given a bunch of training points. You're going to quantify the error on the ith training instance through a divergence function, which is the divergence between the output of the network and the desired output of the network. You compute the empirical risk as the average of these divergences over all the training instances. We will also call it a loss. This is a term that you will keep encountering. Now observe that I'm already given the x's, I'm already given the d's. So the only term that remains that can be modified, the training data are given, right? So the only term that remains that can be modified is this weight. So the loss function over here is actually a function of only the weight. And we're going to estimate the parameters of the network to minimize this empirical risk or the loss. So our estimated parameters are the weights W that minimize this average divergence over all of your training samples. And the hope is that when you do that, you will actually be minimizing this guy. This is a hope. There's no guarantee that it's going to happen. And that is how we will train our network. So again, we're going to actually call this empirical risk a loss. It's a terminology you'll repeatedly encounter in the deep learning literature in general. Again, keep in mind that the loss is an estimate for the expected divergence, which was the shaded area in our figure. And what we really want to minimize is the shaded area. The loss is an unbiased estimate of the expected divergence, which is why we sort of assume that minimizing the loss will also minimize the expected divergence. The key point to note here is that since our training set is given and thus fixed, the loss is only a function of W. So we can minimize the loss, right? And so here is the final problem statement for learning. We are given a set of, a training set of input-output pairs. We will construct a loss function as the average divergence over the training set. For a given training set, the loss is actually a function of just the network parameters. We will minimize the loss function with respect to these to W. This is an instance of function minimization or optimization. So here's the story so far. We learn networks by fitting them to training instances drawn from a target function. Learning networks of threshold activation perceptrons requires solving a hard combinatorial optimization problem. Instead, we use continuous activation functions with non-zero derivatives to enable us to estimate network parameters. We define a differentiable divergence. This divergence must be differentiable. Again, we will see why. Between the output of the network and the desired output of the network for training instances. And then we optimize the network parameters to minimize this error. So this is an instance of function minimization. Right? Questions? Any questions, guys?
Yeah, I have a question actually.
Yeah.
So the difference between the true and empirical risk is that we call the variance.
No. The difference between the true and empirical risk is the true risk is what you want to minimize. You don't know it. The empirical risk is what you compute. The variance, when you're speaking of the variance, it's a different uh, thing altogether. So let's say you chose 10 training samples. Every time you choose 10 training samples, then the empirical risk you get from the training samples is going to be different, right?
Right.
So the variance in the empirical risk that you get across these different experiments, and where in each case you draw 10 samples, that is your variance. That's what we speak of when we speak of variance.
So basically, if we are like conducting 10 experiments, the difference between the outputs we are getting in different experiments, that is the variance.
The difference between the losses you get, that's going to be the variance of the loss, and you'll have variances of other terms as well.
So like, do we have any term for the difference between true and empirical risk? Let's say we are actually minimizing the empirical risk, but actually the true risk is not getting minimized. So do we have?
So there is the true risk, and that's almost certainly going to happen, right? There's a ton of literature on trying to find out how much the true risk actually goes down when you minimize the empirical risk. And the reason for this is this, that when I've got is my training samples over here. I don't have anything else, right? And my function that I'm hoping that it actually learns this function g of x. But because I've only got these guys, I have no guarantee that it's not going to learn something like this, right?
Right. Yeah.
And so that's a problem we're always going to deal with, and that's a challenge.
So in this case, when we experiment on the test set, that the error will be too much, right? So can we call it overfitting?
This is overfitting overfitting is a very dangerous term. You can call it that, right? But again, a lot of stuff that you hear about overfitting, and especially in casual conversation, is flat out wrong. Okay, so be very careful in using that term.
Sure. Thank you.
You're doing this is the only information that you currently have. If this is the only information you currently have, then if you were actually minimizing your loss perfectly, what kind of function would you learn?
If we are actually minimizing, then the same curve as the one above.
No. Any curve which goes through these is going to minimize the loss, right?
Yeah, right. Yeah.
And you need additional criteria to choose between those.
Okay.
That's all. But you always want to overfit, meaning you always want to nail these things. If you're not nailing these things, then even the little bit of information you have, you're not using fully.
Right. Thank you, Professor.
Yeah. Any other questions, guys?
Sir, I have a question.
Yeah.
Could you please explain how the divergence is computed?
The divergence is something that we're going to go over in the next class. I'm actually like 20 minutes behind in today's class, so my lectures are going to slide, unfortunately, but that's the way it is. The divergence, there are many different divergence functions. How we define the divergence is an issue in itself that we will discuss in the coming classes.
Okay, thank you.
Right. Anything else, guys? Okay, Yiming, you have your hand raised. No? All right, so guys, I was expecting to finish the next 17, 16 slides as well. But obviously you guys have a class to go to. So I will drag this. What I'm going to do is my nicely organized lectures are going to go kind of bonkers. And so I'm going to complete lectures 3, 4, 5, and 6, 3, 4, 5, 6, 7, and 8. And at the end of the 8th lecture, which is the last lecture on training, I will record an extra lecture, not in the classroom, completely independently, and I'll put it up and I'll expect you guys to watch it simply because I'm falling behind. Okay. So if you have any more questions on today's material, post it on Piazza. I'll sit here for a while if you guys want to ask questions, and we'll stop the recording in about 2 minutes. So any more questions?
Sorry, could you? Oh, sorry.
Yeah.
Is a question for like designing the loss, designing the divergence like the same thing as we design for the loss function?
The divergence, the loss function is composed from the divergence, right?
Yeah.
So here are the criteria. We want 2 conditions, okay? We want, what we will see in the next class is this, that we're going to use gradient descent, right? So let's say I have some parameter W, the weight of one of the neurons in my network, okay? I want to compute how changing W by a small amount changes, loss. Does increasing W decrease the loss, or does it increase the loss? Now, these are the questions. This is basically the basic procedure we're going to use is throughout training is to come up with a way of deciding whether perturbing this W in an upward direction increases or decreases the loss. If perturbing it in an upward direction increases loss, then you're going to perturb it in the downward direction. If perturbing it in the upward direction decreases the loss, you're going to perturb it up, right? Now, in order to be able to do that, you need to be able to decide how much perturbing this guy perturbs the loss. And that computation is only possible if this loss is differentiable. For the loss to be differentiable, the divergence must be differentiable. So the criteria we're going to use is that A, the divergence is differentiable. B, the divergence is always non-negative. And when your desired and target outputs are identical, the divergence must be 0. So the loss floors out at 0. This property is what we will use. And besides that, exactly which divergence you choose, that's a different question. We'll actually address this in class in a couple of lectures.
Could you also show again the derivation that you wrote down when you were explaining how the expected value can be empirically estimated?
I'm saying the empirical, so if I've got, let's say I have some n samples, so my empirical loss, right, is 1 over n summation I, the divergence between f of xi, I'm not writing the w, and the target. What is happening? Go away. Okay. Pardon my whiteboard. Okay. So when I take the expectation of the loss with respect to x, this is going to be the expectation of 1 over n summation I divergence of, I just call this divergence of xi for just for brevity, right? But then the expectation function is linear. So this is simply going to be, operation is linear. So this is simply going to be 1 over n I expectation of the divergence of xi. And if I'm thinking of this in a generic sense, across different experiments, xi's will change. So in that case, xi is a random variable. So and this simply becomes the expectation of the divergence in general, right? And this is not a function of x anymore. It's the expected value of the divergence. So this is simply going to be 1 over n summation I, the expectation, which is not a function of n, of the input. So which is, I'm summing it n times, so it's 1 over n times n of the expectation, and these cancel out, which is the expectation. It's a bit of funky little math, But not too complicated, but the point really is this. What does this really, really mean? That is more important. So what this means is this. I'm going to try this. Whiteboard of mine is pretty miserable. Okay. Let's say I have my target function, g of x. And then I have my, this is the function that the network is actually computing. This is f of x, okay? Now, suppose I take some set of, say, 3 samples, okay? Then the loss is going to be the average of these 3 lengths. Now, in a different experiment, I take, say, a different set of 3 samples. So in that case, the loss is going to be the average of these 3 lengths, correct?
Yeah.
Every time I run an experiment, the loss I compute is going to be different. It just turns out that the average of all of those losses is the same as this area. It doesn't mean the losses are all the same. It means that across billions and billions of experiments, where in each experiment you pull out 3 samples and compute the average divergence, then across all of those experiments, the average loss is the area that you're trying to estimate. It doesn't mean that in any single experiment, the average of these 3 guys is that area. That make sense?
Yes. But how, like in the blue, can you go up a little bit?
Yeah. Yeah, okay. Oh, come on. Yeah. This one? Is this what you wanted? I think she's muted.
Sorry, I was disconnected for 1 second just now. Did you omit the D at the back of the divergence?
So did I omit what? Pardon me?
There is a D term there, like the G of X or something.
So this one, I'm just being lazy. When I say div f xi, this is just the divergence between f of xi, which is what the network is computing, and the desired output for xi. Right?
Yeah.
In the end, it's just a function of xi. So I'm just using a shorthand. Being lazy. Right? Because f is a given network, d is a given function. So eventually it's just a function of x. Different x's will give you different divergences.
Thank you.
Right. So whether he stopped the recording?